Hello, everybody, and welcome to Denied Access Science Podcast. Today's topic will be the solar system. So, first, we're going to talk about the solar nebula theory. Now, the solar nebula theory tries to explain how our solar system was formed. Now, this is a process that, keep in mind, occurred very long ago. But let's start. So, as background information, to create a solar system, a supergiant star explodes at the end of its life, releasing gas and dust. This gas and dust creates a nebula. And for an example of this, you could imagine a mumble jumble of Legos dropped onto the floor. It shatters and places randomly Legos all around. Now, when this nebula is created, which is formed from all this gas and dust that was released, eventually it'll collapse. The temperature will increase very hot, and it'll start spinning very, very fast. And this, keep in mind, is in a counterclockwise rotation. So, when the nebula spins enough and gets hot enough, it will flatten into a flat disk. And this will then create outer rings. Now, in these outer rings are planets, and there will still be a tiny pile in the middle, and that'll be your star. Now, these planets on the outside ring are two main types. The two types of planets are terrestrial planets and Jovian. Terrestrial planets are like inner, and they're a lot denser and they're closer to the star. Jovian planets are less dense and further. On these outer planets, there are lighter elements because they are not as close to stars, so there's not as much gravity fusing. And the gravity pulls these heavier elements closer. Now keep in mind, planets don't just immediately form. They have to go through a process called accretion. Accretion is where, basically, imagine spraying drops of water down onto a sheet of wax paper. And if you're rotating the wax paper all around, tilting it, the water is going to collide together and generate bigger droplets. And that would be called planetesimals when they get bigger. Now these planetesimals collide with other planetesimals, and they create bigger planets and moons. And these planetesimals are a lot of gas and dust, basically. Now, some really astronomically savvy people might know that, but Venus rotates backwards, and Uranus is on its side. So how did that happen? There's this period of bombardment, known as bombardment, where these planetesimals are colliding heavily into each other. And these planetesimals can generate enough force upon collision to completely turn planets. So I want you to imagine Uranus rotating on a plane, on an axis, just like every other planet. And then a big planetesimal comes and it knocks it onto its side. That's how Uranus got its rotation. Now, Venus rotates completely backwards, so a very large planetesimal would have had to collide with it, and this planetesimal would knock it. Now, we're going to explain the concept of solar wind to you. Once all these planetesimals are created and are colliding, they'll start to orbit. And when they orbit, they're stable, basically. So, solar wind, which has always been there, it starts more heavily clearing out the gas and dust of the solar system. So there's not a lot of gas and dust in there. And that's how we have, the Kuiper Belt and the outer planets. So I want you to imagine a fan as the sun, pebbles as the terrestrial planets, balloons as the Jovian planets, and paper towel pieces as leftover gas and dust. Now the air from the fan is solar wind, and they're going to push away the gas and dust out of the way so that there is not a lot of gas and dust left. Thanks for sticking with us here in Denied Access Science Podcast. And now we're going to be talking about Kepler's laws, Newton's law of universal gravitation, and planetary motion. So rotation means spinning on axis. Revolution is traveling around like a center point. And an orbit is the path a planet takes as it revolves. So Kepler's first law. Well, basically Kepler's first law explains that planets orbit their star on an elliptical path, an ellipse, which is basically a fancy word for oval. Now, the sun, or the star, is at one focus. So, foci. And how ovular the orbit is called eccentricity. So if I have an eccentricity of 1, I'd have a perfect line. And if I had an eccentricity of 0, I'd have a perfect circle. And it ranges from 0 to 1, so it can't really be over a perfect line or over a perfect circle. Earth's eccentricity is 0.02, and the aphelion is the farthest away point from the sun, or the star, and the perihelion is the point closest to the sun. Now, Kepler's second law is equal orbit areas in equal time. So, no matter how far away you are, either at your perihelion or at your aphelion, it's going to be equal time and an equal orbit area. It's like, imagine a slice of pizza. These two pizza pieces might not look exactly the same, not in size, but they have the same exact area. So if you put 43 pieces of pepperoni on one, then you put 43 pieces on the other, and you can't fit any more, they're equal. So Kepler's third law, an AU, which is an astronomical unit, it's used to measure distances, and 1 AU is the distance from the sun to the Earth. Now, the closer the AU is to 1 or is to 0, the shorter the year it is, and the further is the longer year. So Jupiter might be 30.5 and Mercury might be 0.24. So Mercury would therefore be closer than Jupiter. Now, this is probably the most complicated law if you are a very visual learner. So imagine 1 AU. Now, that 1 AU we're going to imagine in like layman's terms. So 1 inch might be 1 AU. So there are 3 planets in front of you. One is a Jovian. It looks farther away, and you can tell that, but you need to prove it. And there's a terrestrial, and it looks closer, but you still have to prove it. So you're going to take that ruler, and you're going to count how many AUs, or inches, in our scale / model, it is away. Now you're going to see that the Jovian, because it's farther away, it's going to be more AU than the terrestrial. Now moving on to Newton's law of universal gravitation. The force of attraction between two objects. So when you're closer to, let's say, the sun, you're going to go faster. When you're further, because there's less gravity, you're going to go way slower. That's why Neptune's orbit doesn't take the same amount of time as Mercury's, because Mercury's closer to the sun than Neptune is. And measuring mass. More mass means you have more gravity. There's more stuff pulling matter towards you. And that's why if you have a weight that is 150 pounds and you drop it from 10 feet up, it's gonna fall faster than, let's say, a 5-pound weight. Now, these do not apply in 0 G's at all. That is the same, really. But we're going to move on to our next subject. Now, here today, we're going to clear up some misconceptions. So, sometimes you might hear people say their year, or you might hear their orbital period, when they're describing how long it takes for a planet to do a complete rotation. Some of these terms are more correct than others, I'd say. You wouldn't say, oh, this planet has 900 days more than what my planet does. You'd say, this planet has a longer orbital period than the planet that I have by 900 days. Thanks for listening to Denied Access Science Podcast. See you next week.